So in this video, we will see perovskite. So perovskites are nothing but of the formula or of the type ABX3. So they are basically cubic unit cells. Here A is strontium, B is titanium, and X is oxygen. So this is the common representation. It is a primitive cubic unit cell with oxygen at its centers, and this titanium and zirconium can be either at body center or corners. Okay. Uh, Now the titanium. So if we consider this thing and writing, so titanium oxygen bond length is, of course, if the side is A, it is A by 2. That is found to be 1.9. Strontium is equidistant from 12 oxygen. Strontium in a sense, okay. These are the two either forms. Okay. It can represent perovskite either this way or this way. With concern of this way, I am writing the informations. So titanium oxygen bond length is A by 2, which means this bond length. And strontium in the sense the center atom, strontium is at the equidistant from this 12 oxygen, corners of the cubes. Now strontium oxygen distance is half the diagonal of cell face, right? This will be the half of the diagonal face, right? That is A by root 2. You know the following things, that earth cell is A, then for a body cell it is root 3A, and for a face it is root 2A. So by considering these values, we can write that strontium oxygen distance is A by root 2, which is about 2.7. So each oxygen has two titanium at its nearest cationic neighbor of distance 1.9, and 4 strontium coplanar with oxygen at 2.7. That is the conclusion of these things. So that is the strontium. Each oxygen has 2 titanium in its surrounding with a distance, inner distance, cationic neighbor of a distance 1.9, and each strontium, 4 strontium, that in the face, 4 strontium is coplanar with the oxygen at 2.7. So it is debatable whether oxygen or cyanide is best regarded as 2 linear or 6 squashed octahedron or 14 6 cation. Okay. Perovskite contains oxygen at face center and strontium at corners, right? So structures of mixed strontium oxygen CP layers in perovskite is such that 1/4 of atoms are strontium arranged in a fashion. 1 strontium atom strontium. So you know that layers, you're not considering the center. We are considering just the we are not considering the corners. We are just considering strontium and oxygen. So while looking the structure, you'll understand that it is made up of actually strontium, oxygen CP layers, like close packed layers, and it such a way that 1/4 in a sense. Okay, if we consider a portion, and we can see it is just strontium oxygen CP layers. We are just not considering the titanium center, body center. So we just understood, okay, fine, what we are just CP, close packed layers. So if we consider the strontium and oxygen only, then we can say that 1/4 of atom. So perovskite is a framework structure of it, corner sharing K6 octahedra, titanium oxide octahedra, and with strontium in 12 coordinated indices. So we have other perovskites also, right? So some more details that we will consider in this titanium or strontium oxide perovskite is that oxygen of the octahedra. Okay, here we consider this titanium O6 as an octahedra with the strontium in 12 coordinated indices, like. So here the oxygen, each oxygen of octahedra is shared with the one other octahedra. such that titanium, oxygen, titanium arrangement is linear. Like these octahedras are held together. So titanium, oxygen, titanium, this forms a linear structure. So each oxygen is shared with the adjacent coordination octahedra. Thus, octahedra link off their corners to form sheets and neighboring sheets link similarly to form 3D framework. So we can say that octahedras are how this octahedras, titanium, oxygen octahedra is linked to form a 3D framework. Basically, it is these octahedras are linked off their corner to corner to form a sheet, and neighboring sheets together we will get a 3D framework. So variety of distorted non-cubic structures exist. These lower symmetry structures often form on cooling high temperature cubic structures and frameworks of octahedra. So they will be getting distorted. Distorted non-cubic structures actually exist, and these non-cubic structures, they have low symmetry. Like so, on cooling and all, we can cooling at high temperature means at a very reduced temperature. These cubic structures of octahedra or framework. The cubic structure and a framework of octahedra, it may be slightly distorted, but we can make it. Now comes the tolerance factor. So we know in perovskite distortions are common. So reason why structural distortion occurs in perovskite is that the A or B atoms, if we consider titanium as A and strontium as B, it can be eitherly a corner or body, right? So A and B or A or B are not exactly at the right size to fit sites. They generated by remainder of say if we have made a titanium oxygen octahedra, and this strontium should be placed exactly at the site correct way, such that it can form a primitive cube structure. So if there is a somewhat deviation in that position of strontium in that particular site, it creates, sometimes both titanium and strontium can create this, or mostly, okay, it's easy to create an octahedra. So in this case, we create this titanium oxygen octahedra, and placing the strontium, it should be exactly at the right side, so that only we will get a perfect cube. Otherwise, we will see distortion or twisting and all. So that is the reason, or so that is what it points out to tolerance factor. Okay. So in an oxide with ideal cubic perovskite structure, the bond length is related to unit cell dimension as A is equal to root 2 RA2, which is equal to 2 RB2. That is the distance between A and O. This unit cell dimension, bond length A, should be equal to root 2 RA minus O. Okay, just understand one thing, that both the sides should be, if both the sides are perfectly placed, then you should get, if you know the distance between A2O and B2O, and when we substitute here, you should get the bond length. Okay. So and the degree or the ratio of these two are known as tolerance factor. Tolerance factor generally represented by T. Thus, it is the degree to which size depart from disk equation, means it gives the tolerance factor. The ratio or the like comparing both the distance between A to O and B to O with root 2 and 2, we will get the tolerance factor. This difference, degree to which this size deviates or departs, is known as tolerance factor. So we'll consider another perovskite, which is nothing but gadolinium iron O3. So in this gadolinium iron O3, so as we know, we have the structural deviation, and the structural deviation in perovskite is due to nothing but the structural deviation in perovskite is nothing but due to the if A or B or A and B are exactly not perfectly sitting at the site. Okay, they are not exactly the right size. Actually, they are not exactly the right size. If they are not exactly the right size to fit that particular site, then it creates this structural deviations and distortion. So reason for the structural distortion are associated with the size requirements of 12 coordinate A and 6 coordinate sites. That is, you saw that we made a titanium oxygen octahedra, and strontium should be placed exactly at the 12 coordinate indices.